Hi, Boaz. Thank you so much for joining me. I just wanted to start by asking you, how did you get interested in computer science in the first place?
Initially, my dad is an electrical engineer, and he was always interested in computers. So already in 1982, when I guess I was 8 years old, he got a VIC-20, which had, I think, 4 kilobytes of memory, and so I started playing around and programming computers from a very young age. But actually, when I started college, undergraduate studies, I didn't want to study computer science. I thought that it's just programming, and I already know how to program, so I enrolled in mathematics and philosophy. And
Okay.
I just ended up taking a lot of math class with people that were doing computer science, and they were talking about how the great job market is for computer scientists, and how they're going to get all these great salaries. So at some point I said, okay, maybe I'll do a triple major of math, philosophy, and computer science just purely for financial reasons. But then once I started actually taking computer science courses, and I discovered it's so much more than programming, then I was hooked.
So you got involved in this sort of more theoretical side of computer science, but I'm wondering if you can tell me a little bit more about within that, like theoretical computer science, what areas did you specialize in at first in the beginning of your career?
So I initially started in cryptography. So I did my PhD on cryptography and zero knowledge proofs and related topics.
Can you tell me a little bit more about what that entailed at a higher level?
Mhm. So the notion of zero knowledge proofs is really beautiful and counterintuitive. It's about how do you prove that a statement is true without revealing anything except the truth of the statement. And the first question you can ask is, what does it even mean not to reveal anything? And the way that Goldwasser, Mikali, and Rakov, who defined the notion of the zero knowledge, defined it was this beautiful notion of simulation. They said the idea that, say, Bob didn't learn anything from his interaction with Alice is if Bob could have simulated the interaction without having any access to Alice at all. And so that was the heart of the zero knowledge, and it was later extended to many other cryptographic settings. How do you demonstrate that someone didn't gain anything from access to some confidential information? Is we could have simulated the same interaction without access to that.
Mhm.
And the idea of this simulator is typically it needs to basically take Bob, which in theoretical computer science we model as some algorithm, and
Mhm.
transform it into this simulator algorithm. And typically, the way we do it is using a black box simulation. So the simulator just uses the algorithm of Bob as a subroutine or a black box. And I
Okay.
was very interested in whether we can gain something by using the actual code of this party, and not just its and not just calling it as a black box. And that was much of what my research was about.
So that's like very cryptography has a lot of applications, but these are the side that you worked on is very theoretical. There's a lot of proving formal theorems about things.
Yes.
More recently, you've done a lot of work in machine learning, and this is a branch of computer science that's really taking off right now, and kind of
Yes.
where the experimental side, the empirical side, is just kind of way running ahead of the theory. So what
Yes.
prompted this change of focus for you?
I mean, I think it's, yeah, like part of it was happenstance. There was a bunch of graduate students at Harvard that were very interested in deep learning, and I started talking to them just because, just to learn what they're doing, and just because they didn't really have a lot of people to talk to. And and as I was, I was talking to them, and they were explaining to me some of these questions, some of the which I've heard about and I knew about, but I didn't really think about in depth. I started seeing the really intellectual beauty and excitement of this field, and I kind of got hooked.
So how does you think your background in theoretical computer science, like how does that inform the way you think about AI or approach this research?
It's it's a good question, and I think you need to keep some things and lose some other things. So I think you have to avoid the temptation of, when you have a hammer, everything in the world is a nail. So the fact that you are good at proving theorems doesn't mean that you should always try to prove theorems on anything that you see. On the other hand, I think the way that we think about in computer science, in theoretical computer science, the way that we think, we try to separate out what is random and what is adversarial, and which components are controlled by which entity, what could go wrong. Those types of modes of thinking, I think, can be pretty useful also in thinking about AI.
So yeah, I sort of spoke to this a little bit before, but how would you say the challenges in AI research differ from the challenges when you're trying to do theoretical computer science?
Yeah, as you mentioned, this is a very different relation between theory and practice. In
Uh-huh.
cryptography, it's generally been the case that theory is about of 20 years ahead of practice. So Goldwasser, Mikhail, and Rakov were invented zero knowledge in the early 80s, and I think it took really only now or in the last decade, things are really kicking off with people implementing general purpose zero knowledge proofs for various applications, many in blockchains. And that has been kind of a recurring theme where theory shows that something is possible, but initially it's not efficient. And with time, both people are make it more efficient as well as find applications for it. But in modern machine learning, the situation is somewhat reversed.
Uh-huh.
Experiments show that something works, and the theory is somewhat behind in explaining why it works, how to model it, and predict it. And so it's much more, to some extent, it feels much more like a natural science where we discover something and then try to explain it than in a field of constructed science or engineering where we first map
Mm.
it out and then build it.
So I guess I should back up a little bit. So we jumped into talking about AI, machine learning, kind of using these words maybe synonymously, but these words are used for lots of different things from people might have heard of language models like ChatGPT to applications that seem much more mundane in a way, like people say, oh, this AI help me recommend what movie I should watch. So how would you define the distinctions between these terms, and what do you think are the most important distinctions for the broader public to understand here?
So I think to some extent it is accurate to say that um, recommendation engines, image classifiers, and ChatGPT are all forms of AI. The main difference in them is generality. And to some extent, this kind of follows the history of computing, where initially people built special purpose machines that were doing very specific forms of calculations. And then first, theoretically, Turing realized that you can have the universal machines, and maybe even like Babbage realized it even earlier
Mhm.
and tried to build it. And then eventually people built these electronic computers, and later Grace Hopper wrote compilers, and we moved more and more to the world that we have these general computation machines, and think of computation as a general term rather than thinking, okay,
Mm.
this is just designed to do this or that. And I think it's similar with AI. We have these more narrow types of original AI applications, whether it's recommendations or chess or a vision, and now we are moving more and more to the more general types of models that can basically do anything.
So there's been a lot of progress in AI that people have heard about recently. What recent developments have surprised you the most?
In terms of recent developments, I've been very happy with the OpenAI's O1 model that they, or maybe I should say we, should recently released. I think it's been very successful and solving some very hard problems. And generally, I guess if you go a little bit more for the last few years, I guess the main surprise is that basically pouring more computational resources and more data just seems to work. And it's not a given. Like, I think it's often in scientific theories, I think every time you increase like a few orders of magnitudes, the phenomena that you're trying to model, then everything changes.
Mhm.
But it seems that over the last, say, decade, we have increased the size of our neural networks by many orders of magnitude, the size and the amount of computational resources that we pour into them, and the basic things still work. And so,
Mhm.
so that's been surprising.
So tell me a little bit about what you've been working on these days.
So I've had some works on, to some extent, I've been very interested in how do you give some guarantees and properties to AI systems, which does mesh well with my background in theoretical computer science and cryptography. So I've had works on how do you make sure that generative models do not violate copyright, and can you give some kind of rigorous guarantees on the relation between their output and individual data points that they have seen in their training sets. I've had works on studying the feasibility of strong watermarking schemes for generative models, and we had certain impossibility results under assumptions and also some empirical demonstrations. And recently at OpenAI, I've been working on the alignment and safety components, and been involved in the safety training for the O1 preview model and O1 model, and hopefully we will be also publishing more technical reports about this soon.
So yeah, tell me a little bit more about that first thing you mentioned. You said this is really relevant to your background in cryptography is relevant here. How exactly does that come in when you're trying to prove things about, say, how well you can watermark the outputs of an AI model?
So one of the things that I think the cryptography background is useful is even trying to come up with a definition for watermarking.
Mm.
So you need to think of, in cryptography, we always think about Alice and Bob and Charlie and Eve. And it's similar here. You need to think about, okay, what is the adversary? What are the adversary's capabilities? So in terms of, say, watermarking outputs, you think, okay, the adversary is someone that asks a model to generate some kind of output. And you imagine that the person can ask multiple queries to this model. And now you need to say, how do you model the capabilities of this adversary? So classically in cryptography, we say, okay, the adversary can do any polynomial time computation. But that does not make sense here because the generative model itself is polynomial time. So if the adversary could do anything, they could just generate the data themselves and could remove any watermark, or they wouldn't have the watermark in the first place. So we are trying to think of like an adversary that has access as a black box to the model that is watermarked, but maybe only weaker models with available for it to run locally. And then we also try to understand what is the goal of the attack. So I think the goal of is the attack, if you're, say, asking the model to, say, generate an essay for you, you're a student and you're trying to generate an essay to cheat on your homework. So the goal of a watermark erasure attack is not to come up with an identical essay that is not watermarked.
Hmm,
Goal is to come up with an essay that is not watermarked and has the same quality. As long as you get an A, you don't care if it's identical.
I see.
So, if the essay had some kind of rhetorical flourishes or like some kind of we chose a certain chose certain things to focus on that cause the were a function of the watermarking, you can remove these things as long as they don't hurt your grade.
I see. So I imagine that kind of makes it more difficult to prove things. Like if you're trying to prove that two things are like exactly indistinguishable given some resources, whereas here it's sort of a more nebulous category, even what is, in what
Right.
respect are they indistinguishable?
Yes, so you have to kind of like make some assumptions. So for example, in our paper, we said, okay, you have to make some assumptions that you have a notion of quality, and we cannot really model quality of an essay or something like that. So we just say, okay, you have some kind of a quality oracle. You have something that you could query and it would tell you like the grade of this particular output. And then we can work modulo these assumptions. I think a lot of the time, this is what you have to do. In AI, you need to understand which parts you can reason about mathematically and which ones you need to kind of abstract out and say, okay, I have this black box that can do X, and I'm gonna not try to understand how exactly it works because it's a little bit too nebulous.
I see. And so you mentioned you'd prove some impossibility result there. Can you tell me a little bit about what that was?
Right. So we basically proved that under certain assumptions, which some are technical, but basically these assumptions of having a quality oracle, an adversary could erase the watermark while preserving the quality. And I can tell you, like, the main idea was that you try to apply some random perturbations to the output. But generally, applying random perturbations is a very bad idea because it would reduce the quality. But if you do have a quality oracle, then you can try a bunch of things and then only keep the perturbations that still maintain quality. And as you continue this again and again and again, eventually you venture far enough away that even if you can't test, even if you cannot yourself test for the presence or absence of a watermark by some kind of properties of random walks, you can be fairly certain that the outcome that you have is no longer watermarked.
I see. And so what, this is sort of outside the theoretical domain, but what do you think the takeaway points are from this kind of work for how people might want to use these systems in the real world or design them, that is?
Yeah, I mean, I think part of it is like, and again, this comes from trying to define exactly what you want. So I think part of it is having realistic expectations of what you can and cannot hope from watermarking schemes. So in encryption schemes, we typically model it so that even if you had an adversary that invested a huge amount of computational resources, they would not be able to break this encryption scheme. And with watermarking, we might not be able to, or at least under our definition, maybe there will be some other versions, but we might not be able to get like this kind of level of security, and we might want to. But we can. There are what we call weak watermarking schemes that have been known that as long as say the adversaries a way to perturb the output are limited. Say, for example, if it's text, the adversary only changes some bounded fraction of the tokens, then you can actually preserve the watermark. So there are ways to do that, but you have to kind of think if in your application it is reasonable to assume that the attacker is restricted in this way, and if it is, then you can use it.
Okay, so yeah, the other thing you mentioned was kind of alignment and safety, and how do you kind of approach these questions as a like from a theoretical perspective, or where do you have to jettison the theoretical perspective?
Yeah, so I mean, a lot of these things are practical, but I think at least the way I try to approach it is I try to kind of define things. So I don't necessarily know like some concepts in alignment. So people they can define it in different ways, and some ways in which people define it could be very hard to operationalize.
Mhm.
But I try to use this definition that alignment is following human intent. And human intent is specified by some policies or specifications, like OpenAI has its model spec, or other companies have their own versions of this. And the definition of, say, alignment is to try to get the AI model to make sure that it conforms to these specifications.
So yeah, it's hard to make predictions about a field that moves as quickly as AI seems to be moving right now, but I'm going to ask you to try anyway. Where do you think this kind of research is headed, and what are we likely to see in the near future?
Yeah, it's very hard to make predictions. I mean, I would just say that from where I'm standing, I don't think progress is anywhere near stopping. So I think we can expect that, say, if you look 2 years back and see the difference that we have progressed in, from say between 2022 to 2024, then you should expect that in 2026 we'll have made at least that much progress also. And I'm sure we'll discover some hurdles along the way, and I'm sure also there is always some gap between progressing in terms of the scientific field and actually, deploying this in the world. We've seen it with self-driving cars, and we'll probably see it in other AI applications. But I think we have done a lot, say, in the last 2 or 3 years. And by the heuristic that I mentioned, projecting forward, the 2 years from now, 3 years from now, will probably look as different from us today as 3 years back look from now.
Yeah, that's a pretty exciting and also kind of scary prospect. So let me then ask you, what are some other things that have excited you recently in the field, if anything comes to mind?
I mean, I think, I think there's lots of like very like uh, interesting papers. I mean, I think there have been. I mean, there is a question that is not yet resolved, but I feel like maybe we are in a better shape now to resolve it, which is there is a long-standing issue with AI systems of adversarial robustness, where we are building these AI systems. They do very, very well in the average case, but the worst case performance is often pretty bad, in the sense that you could say in image models, it has been well known that you could perturb an image slightly in a way that does not change at all its meaning, and yet the model outputs something completely different. And so far, most of what we have seen in this area has been pessimistic. Like most of the results have been negative. Most of the things have been broken. But I'm actually optimistic that with the additional generality that we have and with a more powerful models, we will be actually able to make progress on it. So this is one area where I'm excited about.
That's an interesting distinction there, I guess, between theory, where people usually have an easier time dealing with the worst case proofs than average case, and here the worst case is giving you trouble.
Yes. Yeah, and I think to some extent, like theory might also play a bigger and bigger role as the as the stakes become higher, and we really do need some kind of guarantees that go beyond average case complexity, because or average case performance, because we are going to deploy these AI models in situations that are higher stakes, and we will need to rely on them in the situations that are very far from their training distributions, that we could not have measured in advance what their performance is. So we will want guarantees. So I think there might be some interesting ways to try to merge together the theoretical worst case perspective and the classical machine learning average case perspective.
Okay, great. Yeah, that seems like a good place to leave off. So thank you so much for talking to me.
Sure, thank you.